Assistant Professor, Saveetha Engineering College, for coming over here to deliver lecture on Beyond the Visible. I think this is the new topic on nanotechnology and photonics. And along with you, I am very eager to hear the lecture will be given by Dr. Silambarasan. And also, I have to thank our secretary, Engineer Gogol, and we have to thank Mr. Dr. Tangaraj from Chairman Salem Local Center for arranging this wonderful lecture for us also. So once again, I thank very much for the Professor Dr. Silambarasan and all the members and committee members, council members joined here, and all the members also joined here for hearing the lectures. And thank you very much, sir. And you are welcome to the uh, board, sir. Thank you. Thank you very much. Google hearing my voice?
Yes, sir.
Okay.
Congrats, sir.
Yes, ma'am.
Introduce the chief. Yes.
Yes, ma'am. Thank you, ma'am. Respected Chairman of IE Tamil Nadu State Center, Dr. V. Karthikeyan, sir. Our beloved Honorary Secretary of IE Tamil Nadu State Center, Engineer Gokul, sir. Joint Secretaries, Tamil Nadu State Center Committee members, Local Center Chairman, Local Center Secretaries, fellow members, friends, students, and Tamil Nadu State Center Office staff members. A warm and cordial good evening to you all of you. On this auspicious occasion, I would also like to extend my heartfelt wishes to everyone celebrating the festival of Ugadi tomorrow. May this festival bring joy, prosperity, and new beginnings to you and your loved ones. It is with great pleasure that we welcome you to today's presentation, where we have to honor of hosting a distinguished scholar and researcher, Dr. M. Silambarasan. Dr. Silambarasan sir holds a PhD in physics from Anna University and currently serves as an assistant professor, senior grade, the Department of Physics at Saveetha Engineering College, Chennai. With an impressive 14 years of research experience, Dr. Silambarasan's expertise lies in semiconductor nanomaterials, nanostructures, and devices for optoelectronic and photonics applications. Throughout his illustrious career, Dr. Silambarasan has been actively involved in cutting-edge research projects sponsored by prestigious institutions such as IIT Madras and Saveetha Engineering College. Notably, his pioneering work includes the fabrication of semiconductor quantum well microtubes, a ground-breathing achievement in the field of nanotechnology. Dr. Silambarasan's contribution extend beyond research, as he is also deeply committed to academic mentorship. As a recognized supervisor at Anna University, he is currently guiding PhD scholars, nurturing the next generation of researchers in the field of physics. An accomplished author and presenter, Dr. Silambarasan has published extensively in international journals and has been honored with the Best Paper Award at both national and international conferences. Furthermore, his expertise is sought after by numerous international journals where he serves as a valued reviewer. Dr. Silambarasan's dedication to advancing scientific knowledge is further evidenced by his establishment of the Center of Excellence in Photonics and Nanotechnology at Saveetha Engineering College, where he has contributed to the publication of 3 national patents. A lifelong learner and educator, Dr. Silambarasan's commitment to academic excellence has been recognized through prestigious titles such as Topper and Top Performing Mentor for NPTEL online courses organized by IIT Roorkee and IIT Madras respectively. Please join me in extending a warm welcome to Dr. M. Silambarasan as he has his invaluable insights and experiences with us today. Sir, the floor is now open for you. Thank you, sir. Silambarasan, sir.
சாரோட ஆடியோ இன்னும் கனெக்ட் ஆகல சார்.
Yes, ma'am. இந்த கேட்டுறேன்.
Now connected, sir.
Yes, ma'am.
Good evening, sir.
Sir, good evening, sir.
Am I audible, sir?
Yes, sir, audible, sir.
I think now it is connected, sir. Shall I start, sir?
Yes, sir.
Okay, sir.
Thank you for joining, sir.
Okay, sir. Thank you, sir. Good evening to one and all present here. Respected Chairman, the Institution of Engineers, India, Tamil Nadu State Center, Dr. Karthikeyan, sir. Honorable Chairman, the Institution of India, Institution of Engineers, India, Dr. Tangaraj, sir, and Engineer Kogul, and all members from the IEI India, Tamil Nadu State Center. Good evening to one and all present here. It's my great pleasure to take this guest lecture on this great occasion. Today we are going to see a journey into nanotechnology and photonics. This is my plan for this talk. I'm going to share an overview of nanotechnology. So in this part, I'm going to give you a overview definition and how can we synthesize the nanomaterial, how can we classify the nanomaterial. So we will see the various development of nanomaterials and nanotechnology up to date. And further, I'm going to give some brief introduction about photonics. So after seeing the photonics, then we will see a small journey into nanophotonics. In this nanophotonics, I will share some current trends and future directions. At the end of the talk, I'm planning to give some current research in our Center of Excellence in Photonics and Nanotechnology at SEC and concluding remarks. Once upon a time, big things are very good. You can see the picture. So the Great Wall of China, Egypt pyramid, and many things we are saying the large things, big things, they are very good. They got more attention. It is once upon a time. But today, smaller is better. When you see you can see this pyramid. This one is the modern pyramid. It is a self-assembled quantum dot of germanium atom on a silicon substrate. So this one is the smaller things, and today it is getting more attention. And you can see these are all atoms. These atoms manipulated and written some characters of Chinese. We can manipulate the atom and we can write our own language, our own alphabets also. So it is happening for today due to the advancement of nanotechnology, and everything we can represent in nanometer scale. Here, a human, the height is 10 to the power 9 nanometer. It is equal to 1 meter, we can represent in the form of nanometer. And the thumbnail, we can represent 10 to the power 6 nanometer. Or blood cells 10 to the power 3 nanometer. And DNA structure is almost 1 nanometer. And you can see the atomic structure. Atomic structure is below 1 nanometer. As far as the nanoscience is concerned, the science, it is the study of structures and materials and the nanoscale, particularly the range of 1 to 100 nanometer. Also, we can study the behavior, phenomena, and its characteristics of different materials between the range of 1 to 100 nanometer. And simply we can define the nano, it is nothing but 1 billionth of a meter. That is 10 to the power minus 9 meter. When you combine 10 hydrogen atom, when you combine 10 hydrogen atom in a sequence, the 10 hydrogen atom, it is equal to 1 nanometer. And these nanomaterials can exhibit enormous attention due to the novel characteristics. When you compare these nanomaterials with the bulk material, then they are exhibit novel characteristics. And also we can tune the property. So whatever the property, so we can tune it. Say for example, mechanical property, suppose we need some hardness, then we can tune the material, then we'll obtain the hardness. Like electrical property, high electrical conductivity will takes place when you tune the property, like the optical property, magnetic property. All the properties can be tunable when you move into nano dimension. And finally, it is a interdisciplinary subject. Anyone can participate this subject, this area of research. Say for example, any science branch, any engineering branch, they can involve this area of research. That is the great advancement of nano. And you can see various graphical representation and the scale, the corresponding scale is here. And further, we can define the nanotechnology. So it is nothing but it is a particle size matters. So we can define the nanotechnology, the conception and creation of functional structures. Further, when you combine many structures, it will form as a device. Then when you combine many devices, then it will form as a system. So the nanotechnology is the conception and creation of functional structures, devices, and systems with the dimensions from 1 to 100 nanometer. In nanotechnology, there are many technological tools are involving to design the material and characteristics. And further, after designing, we can make the production, and simultaneously we can do the characterization of the material, and we can apply some applications. So it is a multidisciplinary subject, nanotechnology. Here, chemistry, physics, biology, engineering, material science, all the branches can participate and make the nanotechnology. As you see here, in nanotechnology, we are using electron beam to study for characterizing a material, we need to use electron beam. So normally when you use normal light, the normal light, ordinary light cannot see the nanomaterial because they exhibit larger wavelength. So nano means we know that 1 to 100 nanometer range, 10 to the power minus 9 meter. This range we cannot see using when we using the ordinary light, but instead of ordinary light we are using electron gun, electron beam. This electron beam can be observed by some anode, then further it can be controlled by electromagnetic lens. This is electromagnetic lens, Then this lens further tuned on the specimen, so we can see the object. So before going to see further development in nanotechnology, let's start from overview of the development and history of nanotechnology. There are many people, they worked in the field of low dimensional systems. They don't know the name of nanotechnology before 60s. Around 1960s, one of the greatest Nobel laureate, Professor Richard Feynman, he gave a talk in California Institute of Technology in the year of 1959. In this talk, he explored the wisdom of nanotechnology. There is plenty of room at the bottom. From his talk, many researchers, they got inspiration, and they start to work in the field of low dimensional systems. And Richard Feynman revealed that we can see the atomic level, and we can manipulate the atom, and we can design whatever we need. We can design the structure. So everything is possible beyond the limit, beyond the visible region. So that is the great source of inspiration for many researchers. And in the parallelly, the 60s, another important iconic scientist, Morse, he explored the Moore's law. This law, it explained the number of transistors will be doubling. He said the number of transistors will be doubling for every 2 years. Almost, you can see the graph, almost it is saturated. So now in the year of 2007, it is saturated. It has happened. In 60s, he predicted, the scientist Morse, he predicted in the 60s. Then in the 70s, one of the important person, Professor Nario Taniguchi, he presented his research outcomes in an international conference. In this conference, he coined the term nanotechnology, and he presented his results. After Richard Feynman and Morse, further Nario Taniguchi, they encouraged for many young researchers for further invention in the field of nanotechnology. Parallelly, in the 80s is most important in nanotechnology, because the parallel development of many instrumentation techniques. So you can see here, in 80s, scanning tunneling microscope and atomic force microscope, everything they parallelly developed. So we can use these microscopic techniques to see the individual atom and nanostructures, and further we can manipulate these molecules and atoms, and we can design whatever we needed, the structure in the range of 1 to 100 nanometer. And further in 90s, the another important milestone is Richard Smalley and Robert Cole. They discovered fullerenes. It is nothing but the family of carbon-based nanomaterials, particularly carbon nanotubes, graphene. These are the major breakthrough in the year of 1990s. And here you can see the diagram. IBM, they developed this structure using manipulation of 35 individual xenon atom. They created this IBM logo on a substrate. So further in the 90s, there are many researchers, they involved to synthesize and characterize the nanomaterials, including nanoparticles, nanotubes, and quantum dots. And they used the synthesized nanoparticles for various applications in electronics, medicine, and material science. So after the 90s only, the current world know about carbon nanotubes. The carbon nanotube people used in 6th century BC, portrays from the period archaeological results. So this paper recently published in the year of 2020. So from the archaeological invention of Keeladi, people reported the discovery of nanotubes in 6th century BC, and this result is available in this paper. And yeah, further in 2000, the year of 2000, so nanotechnology getting enormous attention because it actively allowing interdisciplinary collaborations. So you can see here in nanoscience and nanotechnology, they are actively involving basic science and engineering and material science. Here in basic science, physics, chemistry, and biology, through physics, we'll obtain many kind of applications. Designing the integrated circuits, studying the surface morphological property using physics, and further we can tune the property of material, and we can set many applications like sensors and many applications using biology for medical applications. And here further important breakthrough in 2000 is nanomedicine. So using the nanomedicine, we can do the drug delivery, and we can identify the disease at the earlier stage itself, and we can control the diseases at the earlier stage. Okay. So now in 2010, so the another important advancement in nanoelectronics. So nanoelectronics, you can see this table here, how the electronic components, particularly transistors, integrated on the chip. So every 10 years, we can see the numbers, it is varied. Almost it is saturated here. And further, now people move, the another field is nano electromechanical system, NEMS. In 2010, nanoelectronic getting more attention because they are more smaller and extremely smaller, faster, and more efficient for electronic devices and nanoscale, particularly nano transistors, memory devices, and sensors. Also, the another important emerging in 2010 is 2D materials. So whatever we are developing the nanomaterial, suppose if it is in 2 dimension, then we can make a film, then we can integrate for on a single chip. So in 2010, these 2D materials also parallelly developed for many applications, including optoelectronics, photonics, and energy storage devices. So currently, almost we are in 2020s. So now people using the nanotechnology for the integration of artificial intelligence, machine learning, quantum computing, and robotics. And also people working for the sustainable development and technological development in the field of nanomedicine, solar cell, and energy storage devices, etc. We can find the nano in nature itself. When you see the lotus leaves, the self-cleaning, it will be take place because the nanostructures, they are formed on the surface. And this blue morpho butterfly, it can exhibit these various colors, blue as well as green. So these colors, because the nanostructures, they naturally available, they presented here. And snowflakes, they also formed. We can understand this behavior using nanotechnology. And peacock feather, this feather, you can see the different colors, different color formation. It is interacting with the light. It's look like 2D photonic crystal structure with the dimension of around 10 tens of nanometer thick. And recently, many scientists, they study these properties, natural properties, and they mimic these nanostructures and principles in the laboratories. So further, we can manipulate these structures in laboratory itself, and we can create some novel applications. Now we'll see the classification of nanomaterials. Based on the dimension, we can classify the nanomaterials as 0 dimension, 1 dimension, 2 dimension, 3 dimension. And also we can classify the material based on what kind of material we are using, like carbon-based nanomaterials, metal-based nanomaterials, semiconductors, ceramics, like etc. Here, one dimension means in nanomaterials, they are superior because they are large surface area. They exhibit large surface area to volume ratio. When we reduce the size of the material from bulk to nano, then we can see the large surface area to volume ratio, surface energy, as well as quantum confinement effect. Quantum confinement effect is nothing but the quantization of energy levels. So here, the confinement, based on the confinement, we can classify this material. Suppose the material is confined in all 3 dimensions. All 3 dimensions, their size is lying between 1 to 100 nanometer means, then we can say these material are 0 dimensional material, like quantum dots, fullerenes, nanoparticles. These are the best example for 0 dimension. So these material, they are confined in 3 dimensions. All the 3 dimensions, they are in the range of 1 to 100 nanometer. Then 1 dimension. Only 1 dimension is not in that range. Remaining 2 dimension, they are confined. So like nanotubes, nanowires, nanorods, and 2 dimension. Here 2 dimension, they 2 dimension they are not confined. Only 1 dimension they confined. So we can see the 2 dimension. In 3 dimension, all the materials they are not confined. They are above 100 nanometer, but they exhibit somewhat the nano properties like nanocrystals, the aggregation of many small nanomaterials which create the nano property. Now we'll see the synthesis of nanomaterial. We can synthesize the nanomaterial artificially. So there are 2 steps, 2 methodology we are involving to create these nanomaterials. One is top-down synthesis, another one is bottom-up synthesis. In top-down synthesis, initially material they are in bulk state. So the bulk material can be tuned as a powder. Then further it is processed as a nanomaterial. We can use these methods like ball milling. Ball milling is a mechanical method. In that method, it's like grinding the material. So initially we are taking the bulk material, and in the bowl we can grind the material for some duration and appropriate situation. Then we will obtain the fine powder. This fine powder, it will form as nanomaterial. When we characterize this material, then we know their properties, their like X-ray diffraction, UV visible absorption spectroscopy, photoluminescence, Raman spectroscopy. All these characterization techniques to reveal their characteristics and their properties. Similarly, we can synthesize the nanomaterial using bottom-up method. In the bottom-up method, they are in atomic and subatomic level. The material, the source material, precursors, they are in atomic and subatomic level. We need to build the material as a cluster, then we need to build further as a nanomaterial. Like there are many methods available. Here I am mentioning few methods like co-precipitation method, salt gel method, arc evaporation method. These methods are best method to create the nanomaterial using bottom-up method, bottom-up synthesis. Further, we can synthesize the nanomaterial, 2-dimensional nanomaterial in the range using many techniques like chemical process and physical process. In chemical process, there are many methods like electroplating and salt gel dipping, spray coating, spin coating, CVD. CVD is nothing but chemical vapor deposition. MOCVD is metal oxide chemical vapor deposition. This one is plasma enhanced chemical vapor deposition and atomic layer deposition. These are the various types of chemical process to develop the nanomaterial on a substrate for many applications. Parallelly, we can develop the material using some physical methods like evaporation, sputtering, and in evaporation we can do many things like thermal evaporation and ion implanting and laser ablation, molecular beam epitaxy. Molecular beam epitaxy is one kind of highly sophisticated instrument, and electron beam also can be used to deposit the material. And here sputtering is nothing but when you pass a high energetic ion to the target, then the deposition will take place on the substrate. We can tune the sputtering method using radio frequency or DC sputtering or magneto sputtering. And here few example about CVD. To synthesize a nanomaterial, we can use the chemical vapor deposition method. Here, in this setup, we can create the thin films for the appropriate chemical composition and the temperature and specific conditions. And parallelly, we can create the thin films using physical vapor deposition, etc. In chemical vapor deposition, we can study the different features of nanomaterials. We can study their chemistry, physics, and their features. Whereas in physical method, this one is a sophisticated method. When you make some advanced device, it is more preferable. Then we can study their structure and we can create the material for device applications. Here few techniques for nanofabrications. So nanofabrication, here we can follow many steps. For making a thin film on a substrate, we need to follow these steps like deposition, patterning, lithography, etching, metallization, packing. Here, initially the material, you can see this step 1 thin film growth on the substrate. Usually in electronic industry, we are using silicon substrate. On the substrate, there are some photoresist layers. We can grow the photoresist layers and we can do the lithography patterning as well as lithography, and we can do the etching process. The etching, it may be dry etching or wet etching, and further complete the etching process, we will obtain these structures. So here on the substrate, I created the metal conduct. So further we can do many patterning and we can grow many layers. And this process is called nanofabrication techniques. So in order to create potential devices, we need to follow these steps in order to create sensors and many devices. These steps are most important. And in nanotechnology, the clean room, the environment is most important. So we cannot do the synthesis of nanomaterial in ordinary environment. When you synthesize the nanomaterial in ordinary environment, ordinary lab means their efficiency is extremely low, and it is very difficult to achieve very high efficiency. So we need some sophisticated and highly protected environment. So here airflow and outside dust particle itself, everything is controlled, and proper dress code people used. Before entering the clean room, we need to use all this dress code properly and do some air cleaning. And here airflow is also in laminar flow. The uniform airflow will takes place in the inside of clean room. And you can see this. This is a typical layout about the clean room. There are many sections in the clean room. Deposition section and metallization section, photolithography section. Usually photolithography and the e-beam, they are using yellowish to light environment. And wet chemical, for some doing some chemistry related works, chemical synthesis, we can utilize this area. Okay, this is a typical structure of clean room, and there are many standard in clean room which is used in nanotechnology. Clean room class 1, 2, 1, 10, class 1000, class 100, class 10,000. So class 10,000 means for a volume cube space, the diameter of dust particle below 500 nanometer, the diameter, let us take a single particle, if it is having below 500 nanometer, then the maximum particle is below 10,000 in a volume space. Suppose when you are using clean room class 100 means the maximum dust particle is in the volume cube space is 100. Class 1 is maximum one particle may be allowed inside the clean room. Here highly production and highly standard protocol are following. So we can make the smart devices using nanotechnology. The applications, further I'm moving towards the application of nanotechnology. In applications, we are using many areas. So A to Z we are using nowadays, particularly energy storage devices, defense and security systems, electronics, and many field, biotechnology, textile, agriculture and food, and many field. And recent days, people are developing many kind of nano sensors for industrial, healthcare, security, defense, energy, and environmental applications. And the further slides also we'll see some applications of nanotechnology. And in the year of 2023, one of the most important Nobel laureates, you can see Mogani and et al. They received the chemistry Nobel Prize for the development of quantum dots. Quantum dots, so typically their size is around 1 to 10 nanometer. The quantum confinement takes place here, and they developed these kind of quantum dots for various applications in the field of nanoscience and nanotechnology. And further, I'm going to tell something about the application of nanomaterials. The application of nanomaterials, we are widely using automotive industry, chemical industry, engineering, electronic industry, and construction and medicine. And in electronic industry, data memory, display, laser diodes for communications, fiber for communications, optical switches, filters, and many applications we are using. And automated system also we are using sensors and lightweight materials and etc. And chemical industry, many applications, magnetic fluids and switchable properties. In engineering, we are using widely for many applications. And construction, in building construction, and we are using the nanomaterials. And in medicine, for making the drug delivery and etc. Here further the application of nanomaterials, textile, fabric, making the smart cloths. Nowadays nanocoated, nanomaterial coated cloths are available in market. They are creating self-cleaning. We need not wash the cloths for certain period. So because the nanomaterials they coated, so it is widely used in the field of medicine and operation theaters. And in the energy industry, making solar cell capacitors, batteries, smart batteries, and nanomaterials widely used. And cosmetics, to protect the sunlight and sun production, and many cosmetic items people used. In nanomaterials, further we are using in food industry, household and outdoor and sports area. And here some of the pictorial representation of application of nanomaterials. So here the photocatalytic property of titanium dioxide nanoparticle. So this nanoparticle widely used for self-cleaning process. In this kind of operation theaters, suppose the tiles they are coated with this nanoparticle means automatically they cleaned, and self-cleaning window for dental cleaning, because all the advancement of photocatalytic activities of these nanomaterials. And further, the application of photocatalytic activities of nanomaterials, we can coat on a mirror, then we can control this hydrophilic nature, and further we can utilize for in car and many industries. So up to now, I shared the overview of nanomaterials and nanoscience and nanotechnology and its applications. Further, I am going to move some brief introduction about photonics. Before seeing the photonics, let's start from light. So light is a electromagnetic radiation. We can see usually. So as you see the electromagnetic spectrum, there are many kind of electromagnetic spectrum. The visible region. So this light, how this light is going to interact. So their interaction can be represented many people for many centuries. So the theory of light can be represented even in the ancient time of this 5 to 3 BC, and further light is a wave. So in 1629 to 1695, and the light is a photon. Albert Einstein, he revealed his theory in 20th century. These are the history of light theory and how this light is behave with the matter, which is called optics. So optics is nothing but to study the light and matter interaction. There are many type of optics. So here I am listed some modern optics. Using the optics, we can study the geometrical pattern of light ray reflection, refraction, and how the images are forming, we can study. And here wave optics, using the wave optics, we can study the interference and diffractions. In quantum optics, applying the quantum mechanical principle, further we can control the light and we can study the light and matter interaction in the atomic and subatomic level. By controlling the intensity property, we can study the nonlinear optics, the nonlinear property. And for utilizing the quantum mechanical property and nonlinear optical property for medical applications, which is biomedical optics, medical imaging and therapy. In fiber optics, for high-speed data transfer, for many applications, in gas sensing applications, we can utilize it. In optoelectronics, modern optics is most important in optoelectronics to create the light emitting devices. So what is nanophotonics? Next, we are going to see the journey into the integration of nanotechnology and the photonics. As far as the photonics is concerned, it is the study of the linear as well as non-linear interaction of light and matter in atomic as well as subatomic level. Here we can study their interaction and exploring their various properties and manipulating light in the nanostructured devices. And we can create, using nanotechnology, we can create various kind of photonic crystals, metamaterial and semiconductor nanostructures. You can see this diagram here. The current electronics, nanoelectronics is revealing this area, and plasmonics. Plasmonics is nothing but the interaction of light with the free electron on the metal, which create the plasmonic effect. This plasmonic effect can be used in various applications for many industries. Here, the photonics, this photonics can integrated with this area because their size is nano. Normal photonics, it deals wide area, whereas nanophotonics, it deals the interaction of light and matter in atomic as well as subatomic level. So some of the emerging area of nanophotonics is the size miniaturization. So when we reduce the size, then we can create the monolithic integration of all kind of components on a single chip. And further, this nanophotonics will enabling the enhanced light and matter interactions. When we compare the classical optics and nanophotonics, we can get the enhanced interaction, and this interaction involving high precision as well as high accuracy for creating the nano devices. Further, quantum optical phenomena, which is widely used for in nanoelectronics and nanophotonics, and some of the principle widely used in nanophotonics. One is plasmonic. As I said earlier, plasmonic is nothing but the interaction of light and matter, particularly free electron on a metal surface. Then further, using the nanophotonic principle, we can design the metal lenses. These lenses are extremely small, ultra thin, and we can control their features. And further, we can design various kind of nanomaterials using nanophotonics. And some of the application in modern technology, one is solar energy harvesting. We can harvest the solar energy. I will explain some solar energy related results in the upcoming slide. We can utilize the nanophotonics for data communication system. Here we can utilize these nanophotonics for making the free space optical communications. This is the next generation communication. There are some prototype model which can develop the next generation communication. Say for example, 10 GB per second, we can transfer the data, and we can create some medical imaging, biomedical imaging using the nanophotonics, and we can create the next generation display applications. So in modern technology, so nanophotonics is widely used. Nanoscience and nanotechnology is also widely used. The one of the reason observation for gravitational wave. So in the year of 1916, Albert Einstein, he revealed the general theory of relativity. In this theory, he said the gravitational wave will be generated when two heavier objects interacted with each other. Then the gravitational wave will propagate on time and space. So actually, up to the year of 2015, we don't have much evidence. We don't have the evidence. The first observation was recorded in the year of 2015 using this experimental setup of LIGO. So laser interferometer for gravitational wave observatory. So in this experiment, people used diode laser as well as Nd:Arc laser for creating this light and matter interaction. And here highly precise lenses are used, and highly precise beam splitters are used. For without these nanophotonic components, we cannot achieve these kind of observations till the date. Here in this observation, they observed two black holes. These two black holes, they located around 1.3 billion light year away from the Earth. So due to extraordinary gravity, they merged together and formed as a single black hole. So one black hole, the diameter of one black hole is around 29 times larger than the diameter of Sun. The another black hole around 36 times larger than the diameter of Sun. When they merged as a single black hole, then they formed as a single black hole, and their size is around 60 to 65 times larger than the diameter of Sun. And then due to this interaction, this gravitational waves, they generated and they propagated in time and space. Then our team, our scientists, they recorded and successfully, and we can able to study the gravitational wave with the help of nanophotonics and nanotechnology. And another important application in modern technology is this also another important milestone in the area of nanophotonics and nanotechnology. Here, 2018, the physics Nobel laureates, Professor Arthur Askin, he developed the optical tweezer. This optical tweezer can be used for making the transportation of particle from one place to another place, especially in living organs. In living organs, we can make the transportation of any new tissues or particles using optical tweezer. This tweezer, it was developed by Arthur Askin. He received the Nobel Prize at the age of 96. Similarly, Gerard Moreau and Donna Strickland, these two scientists, they received Nobel Prize for this invention of the femtosecond pulse laser. Usually, the existing technology is nanosecond pulse laser. People use it, but they developed femtosecond. You can see this representation, graphical representation for timing. So the femto, you can see the photosynthesis is taking this time. This femtosecond, this pulse laser, it can save many lives. We can do the many bloodless surgery using lasers. This kind of lasers are giving more advancements and more applications. In further modern applications, recently, in the year of 2022, the Nobel laureates, they already studied the quantum teleportation. Here also, single photon. For the advancement of nanophotonics, they used the single photon. Then they created the entanglement of that photon, and they studied their quantum teleportations. So this invention is widely giving more attention in the field of quantum computing and quantum information systems. And these are all happening with the support of nanotechnology as well as nanophotonics. And another most important recent invention is to study the behavior of electron dynamics using attosecond pulse light. So here, attosecond pulse light used to study the electron dynamics. So all these advancements is happening with the help of nanoscience, nanotechnology, and nanophotonics. So some of future prospects and innovations in the field of nanophotonics is quantum computing, nanophotonic sensors, the optical computing. So almost we discussed the overview of nanoscience and some introduction about photonics and nanophotonics, some modern applications, modern technological applications in nanophotonics and nanotechnology. Further, I'm going to share some recent development in our research center, which is Center of Excellence in Photonics and Nanotechnology. So in our center, we are concentrating different area of research. One is solar cell. Solar cell is kind of device which convert the light energy into electric energy. So here, there are many type of solar cell available nowadays, like first generation solar cell, second generation solar cell, third generation solar cell. In first generation solar cell, widely the silicon based materials are used. Silicon, almost more than 70 years people used silicon crystal, silicon thin film, silicon nano thin film people used in this field. So up to date, around 25% the power conversion efficiency is achieved in first generation solar cell. And the second generation solar cell is semiconductor thin film solar cell. In that solar cell, almost some of the material, they are highly toxic. this toxic material immediately the many scientists they dropped out, and one kind of second generation solar cell, uh, copper indium gallium based the combination, it gives high efficiency more than 30%, but this material highly cost effective, so it cannot be used for commercial applications. So these kind of copper indium gallium based the solar cell widely used for space applications. Recently Chandrayaan 2 and Chandrayaan 3 missions, and our ISRO scientists they used the this second generation copper indium gallium based solar cell they used in that missions. And currently many people they are working third generation solar cell, because in first generation solar cell it is available in market, almost it is saturated, the power conversion efficiency is highly saturated, and the production cost making the solar cell is high cost when you compare the next generation solar cells. So we are concentrating third generation solar cell. In third generation solar cell, we are mainly concentrating the organic solar cell. In organic solar cell, we can develop the organic solar cell for wearable and wearable applications, wearable electronics, and flexible electronic devices. And also we are concentrating perovskite solar cell, creating the perovskite material and utilizing for solar cell applications. In the perovskite solar cell, almost within 10 years, it achieved the almost equivalent power conversion efficiency of, power conversion efficiency means the sunlight into electricity. The power conversion efficiency is almost 25%. So within 10 years, this third generation solar cell is achieved. And here the main problem is stability. When you compare the first generation solar cell, it has many stability, more stability than the third generation solar cell. So we are concentrating mainly for the power conversion efficiency parameter as well as the stability, how we can make the stability for more longer days. And also in our center, we are concentrating making the diode laser, making fabrication of semiconductor diode laser for next generation optical communications, like free space optical communications. These kind of optical communications can be used for many applications, particularly data transfer and secure communication systems. And also we are concentrating making of light emitting diodes, organic light emitting diodes, OLEDs, and light emitting diodes, inorganic materials for display applications. And these two, diode laser as well as LEDs, these two are the devices which receive the electric signal and then they convert the light. So but in the solar cell, it receives the light then convert into electricity. So we are integrating all these solar cell, diode laser and LEDs on a single chip and making some communication applications in NEMS, nano electromechanical system, and micro electromechanical systems. Apart from this device related research, we are also concentrating the synthesis of quantum dots, semiconductor quantum dots, synthesis of nanomaterials, metal oxides, and various kind of carbon-based nanomaterials, and perovskite nanostructures and nanomaterials. We are concentrating to synthesize and characterize this material for various potential applications in the area of energy related applications. And some of our work I'm going to present. And in first time India, we developed the gallium arsenide based semiconductor microtubes on gallium arsenide substrate. So here we create the semiconductor microtube on a gallium arsenide substrate. On a gallium arsenide substrate using self-assembling mechanism. Let us take a bilayer. These are all, let us assume these are all nano layers. The thickness is around 50 nanometer or 1 to 100 nanometer. These two bilayers like A and B. So the material A and B, both are different lattice constant. Lattice constant means the distance between two atoms. You can see the distance between these two atoms. Suppose this line is a one atom, this line is in another atom, means this distance is called lattice constant. When you compare material A and B, material B, it exhibit larger lattice constant. So when you grow this material on a substrate, yes, here using some physical vapor deposition method, we can grow the bilayers on the substrate. Here the substrate as well as layer A both are exhibit same lattice constant, whereas the material B, it exhibit the larger lattice constant. But when you grow on high temperature process, then they grow with inbuilt strain. So when we release these bilayers after grown these bilayers, then when we release these bilayers, the inbuilt strain will be released. So this inbuilt strain will create this structure, this film into many structure. Whatever we need, we can manipulate this structure. So if you want as a tube, then you can create as a tube. If you want as a plate, or if you want a flower, then you can design the lithography pattern, then you can create these designs. And here one kind of model is here the standing plate. This plate, it is placed as around a 45-degree angle. Then it will act as a mirror. We can send the signal through this, and it can reflect the signal, and it will be acting as a mirror. Like we can create many kind of structures. So using this methodology, we developed one project. We completed one project. This project is supported by IIC Bangalore, Indian Institute of Science Bangalore, and we grown these multiple layers on gallium arsenic substrate. So here we introduced quantum well structures. These quantum well structures grown on the substrate, and here this layer is a sacrificial layer. When we complete this growth process, then when you do the further etching process, then you'll obtain the nanotubes and microtubes. So actually this layer's thickness is in few nanometer itself, but when it's formed as a structure, it is elevated into microstructure. In first time in India, we developed these microtubes on gallium arsenide substrate, and we calculated their elevation, the radius of curvature. This radius of curvature is almost good agreement with the theoretical value as well as the experimental value. And this is the typical TEM image of the semiconductor microtube on gallium arsenide substrate. And this is the SEM image, field emission scanning electron microscopic image of our fabricated microtubes. As you see here, the orientation is playing, the crystal orientation is giving the different type of the structures. And we further studied the laser Raman spectroscopy for the optical. To study the optical property, we used the laser Raman spectroscopy for the semiconductor microtubes. And here you can see the single quantum well microtube and double quantum well microtube we used, and you can see their peak position, as growth as well as the developed microtubes, they shifted because the inbuilt strain they presented on the structure, so they are shifted. Also we studied the photoluminescence studies of the fabricated microtubes. Here also the shifting, we can observe the shift based on their inbuilt strain. Apart from the 3-5 compound semiconductor based nano fabrications, we are also we developed some nanoparticles, particularly semiconductor nanoparticles for various potential applications. Here, one among the results are we synthesized metal oxide, zinc oxide nanoparticle, and we incorporated various transition metals. In this transition metals, we can see various colors, and also further slides it represent the X-ray diffraction properties of our synthesized semiconductor nanoparticles. As you see here, these synthesized nanoparticles exhibit strong crystalline property, and we doped the transition metals, and this is the photoluminescent spectra of the synthesized semiconductor nanoparticle. As you see here, the blue emission. So how the blue emission is enhanced for this material. So this photoluminescent spectra further utilized for the application of the display applications, and this is the photoluminescent spectra of our synthesized nanomaterials, and these are their band gap engineering for how it is emitting blue emission, and further this is the typical scanning electron microscope as well as transmission electron microscopic image of our synthesized nanoparticles, nanomaterials. And I said in the photoluminescent spectra of our prepared zinc oxide nanoparticle, they are emitting the blue region. So these results so strongly agree with the CAE color chromaticity, this diagram. As you see here, we can tune their color property by controlling the doping agent, and we can obtain whatever we need. We can design, we can manipulate these results, and we can obtain the whatever we need. Suppose if we need white region, then you can tune, you can manipulate the material, and you can obtain the results as we expected. And one of our recent result is, so we are also concentrating the perovskite oxides. In the perovskite oxides, almost in pure form, we obtained the white region. So it can be used for various potential application in display and lighting. And apart from the nanomaterials for display applications, we also fabricated some organic solar cell. So this is what kind of organic solar cell we fabricated. Simply we incorporated the semiconductor nanomaterials, semiconductor nanoparticles, the standard template of this organic solar cell, and we studied their power conversion efficiency. Almost the power conversion efficiency in organic solar cell is low when you compare the perovskite or when you compare silicon based solar cell. But here we can utilize for flexible application and wearable electronic applications. And in our center, I am the principal investigator, and these are of my profile in various scientific websites. And they are my teammates. So Professor Tetsu Soha from Nagoya Institute of Technology, Japan. He is supporting for many occasions for developing our works, and Professor Saravanan is my PhD mentor, and, and Professor Naoki Kishi from NIT Japan. And recently we are doing some collaboration with IIT Madras, Professor Parasuraman Swaminathan from Department of Metallurgy and Material Science, and from his we are going to do some printed electronics. Professor Swaminathan is offering many NPTEL online courses also. One among the course is electronic device fabrication. How can we develop the integrated circuits using nanotechnology? So this collaboration further we are going to enlighten the printed electronics. And Professor T. Prakash from National Center for Nanoscience and Nanotechnology, University of Madras, is ready to collaborate with us for making the third generation solar cell. and further for X-ray sensing applications. And Professor Sanmugavelu from Sona College of Technology, we are collaborating and we are doing some research for display applications. And Professor Barnidharan from Saveetha Engineering College, my teammate, and we are doing many research works through the center. And Dr. Ranganathan from Saveetha School of Engineering is working in the area of semiconductor nanomaterial based fiber optic gas sensors. And recently we are concentrating for fiber optic gas sensing applications. And Mr. Akash, he's a PhD scholar. Under my guidance, he is doing PhD in Saveetha Engineering College in full-time mode. And Mr. Anand from SRM University, we are making the perovskite oxide material, and we are studying their optoelectronic applications. And some undergraduate learners, Shankari, Maunika, and many learners, they are following our research, and we are giving some task to them. They are following the research, and they are our teammates, and these are our collaboration and facilities. And further, for any scientific invention and any science related research, so Professor Nobel laureate Tasuku Honcho, 2018 Nobel laureate of medicine, he shared his experience in science in the name of 6 C's: curiosity, challenge, courage, continue, and concentration and confidence. Without these six C's, it is very difficult to get the success. And I would like to acknowledge Nagoya Institute of Technology, Japan, Sona College of Technology, Salem, Center for Nanoscience and Nano Technology, IIC Bangalore, Indian Institute of Science, Bangalore, ATR Wave Engineering Laboratory, Kaito, Japan, Saveetha Engineering College, Chennai, IIT Madras. Any questions? Yes, sir.
Thank you. Thank you
Hello.
so much. Is there any questions from our
Yeah.
members?
Just 1 minute. Hello.
Hello.
Yes, sir. You can introduce
Yes, sir.
and you can give your question.
Am I audible?
Yes, sir. Yes, sir.
Yeah.
You're audible.
Very nice and erudite lecture. But I don't know how many people are able to absorb this, because our knowledge is limited in this nanoscience technology. And it is merely, I can say, is a gray area for
Yes, sir.
non-electrical people. I myself is an electrical engineer. Of course,
Okay, sir.
I've studied half a century back, and I'm 73 now. My
Oh.
question is,
Okay, sir.
say you simply said this nanotechnology is a volume to surface ratio. Yeah.
Yes, sir.
That is
Yes,
the
sir.
essence of this nanotechnology. I'd
Yes,
like
sir.
to know, you elaborated on the solar cells, but
Yes, sir.
nowadays, this is the climate change, global warming. The world
Yes,
is
sir.
moving towards EV vehicles. So
Yes, sir.
I
Yes, sir.
come to know that the batteries now, through this
Batteries.
nanotechnology, the
Yes, sir.
charging cycles are increased, so that the battery need not be replaced for the lifetime of the vehicle. And
Yes,
that
sir.
is the condition that it has advanced in
Okay, sir.
battery manufacturer. That is one aspect of it. Secondly,
Okay.
and the production aspect, you mentioned in your speech, TiO2,
Yes, sir.
titanium dioxide,
Yes, sir. Yes, sir.
that is used in welding electrode, the flux. Is
Yes,
there
sir.
any qualitative change by using this nanotechnology in this process? And thirdly, in medical field, see, I maybe if I am wrong, please correct me. This
Okay, sir.
nanotechnology is used to target the point of delivery of the medicine.
Okay.
So that the other parts are not affected, only the so defective parts or the unwanted cells
Yes,
that
sir.
has to be removed is targeted by this nanotechnology for delivery of medicines.
Yes, sir.
Though I have many questions, I confine to these
Yes, sir.
three purpose of time. Thank you.
Okay, sir. First one is the large surface area to volume ratio. For here, the basic science, it gives the advancement of nanomaterials because of large surface area to volume ratio and quantum confinement effect. With these properties support for tuning their property, manipulating their applications, the material, and we can target the applications. And here you asked the batteries. The batteries, we are studying their applications. Recent days, people planning to work in the area of sodium related batteries. Already the lithium ion batteries, they are existing and they are saturated, and using the nanotechnology, and some of the team, they are developing seawater based batteries. More amount of sodium is available, so they are planning for the next generation related development. They are creating the batteries. And your another question is, when we pass the drug on our body, how it is focused the particular area. Yeah, there are many parameters people are optimizing by doing some simulation and using many trial and error methods. They are optimized, and after doing many further process, we can control for say for example in that light femtosecond pulse laser. When we use the nanosecond pulse laser, it can create heat, so it affect the tissues, whereas the femtosecond pulse laser can be executed the treatment exactly what we expecting. So like people, the time and people working towards the sustainability. Yes, sir.
And one thing you have left this TiO2, titanium
Yes, sir. Yeah,
dioxide, that is used
TiO2.
in
TiO2. Yes,
fluxes
sir.
in the building electrodes. Is there any
TiO2,
qualitative improvement because of this process being shifted to nanotechnology?
yes, sir. Yes, sir. Actually, by controlling their size, people are studying their applications. Widely, we are using in, say, for example, in cleaning water purifications. So in water purification also, we need to optimize various parameters, how it is highly, the pH value, and many parameters. So it is still in research, sir, and people are working, and many applications people achieved using TiO2 based photocatalytic applications. In particularly in solar cell. Solar cell is also dye-sensitized solar cell. On another third generation solar cell is dye-sensitized solar cell. In the dye-sensitized solar cell, highly used for TiO2 for these photocatalytic applications.
Okay, thank you. Thank you very much.
Thank you so much, sir, for your valuable feedback.
Any questions from members? Google?
Sir, yes, sir. I think no
Otherwise,
questions from there.
I think the questions are now less. Anyway, Dr. Silambarasan has did a extensive research on various materials using the nanotechnology. And he has given a very good lecture, giving the example citing in then and there also. It's a very good, nice lecture, sir. It is a very useful lectures, and we conducted a lot of lectures. And this is one of the very important lectures we have conducted in Institution of Engineers. And thank you, Dr. Tangaraj and Ilango and Gogol and other members, those who are supporting us for conducting this kind of lectures. And especially to my on side, did you touch upon the sports devices, sir, using any nanomaterials?
Yes, sir. For the cloths and
Yeah.
many that tennis ball itself, people used nanomaterials, and many indoor games related products, people concentrating in nanotechnologies.
So the nanotechnology is being used in the sports also to reduce the weight of cricket bat and hockey bat also. So they're easy to handle the devices also. And one of the most thing Dr. Kalam researched that the prosthetic leg, that is leg, the artificial leg is very high end of weight. And in order to reduce the weight of the artificial leg, he has used some materials that is being used in place also. So that also here being used to reduce the weight of the artificial leg also. This is a wonderful lecture, sir, and amazing and awesome. Thank you very much on behalf of the Institution of Engineers.
Thank you so much, sir. You are always a great source of inspiration, sir.
Yeah.
So I was from.
Thank you very much. And Dr. Sarodan, I think he is your mentor, and he has worked in Sona College of Technology some years. Where is he now, sir?
So I think he's doing some business, sir. He's in India only, sir.
He is in Chennai or some other place?
Now in Coimbatore, sir.
Oh, he's settled in Coimbatore.
Yes,
so
sir,
thank you very much. And we will move on to the vote of thanks to Mr. Gogol, Engineer Gogol, I think. Thank you, sir. We will meet in person also. Now I am in USA, so that is why I could not able to immediately pick up. Anyway, they have given a message right time. I got it. Thank you very much. You have extensive research, you did it, and extensive materials collection, research collection. You did a very wonderful lecture, sir. Thank you very much. Thank you very much.
Thank you so much, sir.
Thank you.
Yes,
Gogol, please.
I think it's a very a good lecture. We got it from Silambarasan, sir. Definitely, it's eye-opening sessions for the So I thank our maybe our speaker who have given a beautiful lectures on the nanoscience, and also our chairman and our committee members who have been joined here, and all the students, members and faculty members who have taken inspiring knowledge about this nanoscience, because it's upcoming technology where it's going to bind with all the engineering discipline. So definitely, he has narrated a very beautiful case studies along with the solar and also his research area. So definitely, I think this will be helpful for the upcoming research, the students as well as for the faculties. So I thank all the members, and also I thank our staff from our IEA, on Alagradi as well as Lalita, who has taken a huge effort in making this lecture successful. Thank you so much. So shall we complete, sir?
Thank you, sir.
Yes, sir.